afternoon, and welcome to everyone to this new event of the EMS Webinar Series. Let me start by noting that this webinar is being recorded and will be published on the EMS YouTube channel. Please send your possible suggestions of new topics and speaker to us. Whatever topic you may consider could be attractive, I'm sure it would fit in this format. A few words about formalities. First, we'll have a presentation delivered by our invited person, roughly 30 minutes, and then we'll invite for questions from the audience via the chat function that will be only seen by the panelists. Please use this chat to write your questions. Also by raising hands, clicking on the corresponding icon in your screen. In this case, turn your micro on, and if you wish, your camera. And now we turn to our today's speaker, who is Irina Sandu. She is director of Destination Earth at ECMWF. Destination Earth is the flagship initiative of the European Union to develop a digital twin of the planet Earth. Prior to taking the lead of this initiative, she in summer past year she was appointed as science lead from January 2022. Irina joined ECMWF in 2010 as a scientist working on representation of turbulence, and then she led the physical processes team for several years. His career background includes her PhD at Météo France and the University Paul Sabatier in Toulouse, and a stay of a few years, a couple of years at the Max Planck Institute in Hamburg, and many other merits and recognitions that we are not going to mention here. Today, Irina will present a very challenging topic. The title is Numerical Weather Prediction at the Crossroads: How the Quiet, Digital, and Data-Driven Revolutions are Shaping the Future of NWP. Please, Irina, thanks for giving this presentation, and please go ahead with it.
Hello, thank you very much, and glad to see so many colleagues that I know since a long time attending this seminar, and I'm very pleased to see it's well attending. Thank you very much to Ernesto for having invited me to give this challenging talk, and Ernesto proposed the subject, so I accepted the challenge, and I thought it would be very good it's a timely moment to discuss about where are we in NWP, and I frankly believe we are at the crossroad, and what is next. And I will talk about, as you will see, the three revolutions, what we call in numerical weather prediction, and there are revolutions within revolutions, but these are the main three ones from my point of view, by giving examples of work we have been doing at the European Center for Medium Range Weather Forecast, together with many of you in our member and cooperating states. So why are we at the crossroad? Because we are still continuing on the quiet NWP revolution. The digital revolution is amplifying, and the machine learning revolution. I don't even know if we should call it a revolution or utterly really an explosion in the last couple of years. So I'll give examples. I'll talk about these three revolutions, and then I'll end up by talking a little bit about what is next by taking the example of Destination Earth, which is really synergizing these three revolutions. So what do we term as the quiet revolution? It's really this gradual increase in the scale of medium-range weather forecasts, but more broadly in the quality of weather forecasts overall. I'm fairly sure that many of you know this plot. It shows the increase in scale as measured by the anomaly correlation of the geopotential height at 500 hectopascal from the ECMWF forecast. That is from our deterministic forecast. And just to introduce this plot a little bit for those of you who are not familiar with it, that the different colors show a lead time of 3 days, in blue 5 days, 7 days, and 10 days. And the thick line shows the north hemisphere, and the thin line shows the southern hemisphere. And this is what we term this gradual increase. We call it a quiet revolution. And you might have seen a paper by Peter Bauer et al. In 2015 now, so it's almost 10 years ago, coining this term of quiet revolution. And it's really quiet revolution because it's a steady accumulation. It results really from a steady accumulation of the scientific knowledge and technological advances over many years, and is really coming from improvement in the different components of a numerical weather prediction system. And I'll talk about that a bit more in detail now. So if you look at this plot now in more detail, basically what we say is that forecast days have improved roughly at a rate of 1 day per decade. That means, as you can see here on the left-hand side, that forecast 5 days ahead are now as good as forecast 3 days ahead. And what contributed to this is really all the combination of key NWP ingredients, is the science, is the physics, the numerics, the uncertainty, the model uncertainty, the data assimilation. It also increases in resolution, going towards more and more coupled Earth system models. It's really the satellite and conventional observations and their use, the improvements in this, and this experienced a revolution in their own as well. In particular, the use of the satellite, the advent of the satellite era, but also the combination with the 4D VAR, the four-dimensional variational data assimilation that we use at ECMWF, but also in other major NWP systems. And in particular, you see this between 95 and 2007. And you really see this convergence. This is also translated, it's also due to this convergence between the southern hemisphere and the northern hemisphere. Obviously, before the satellite era, the southern hemisphere was much less observed. So we can't attribute, it's hard to attribute the jumps and the increases to various components of the system, because when we develop NWP systems, we really change different components at the time, but it's really these gradual changes in all the components that brought the quiet revolution. And of course, initially we were doing deterministic forecast, but more and more we moved towards ensemble forecast, and ECMWF now only does the 9-kilometer ensembles today. And the improvement in the NWP systems brought not only an improvement in the skill scores for deterministic forecasts, but also for ensemble forecast. And you can see here the gradual increase. This is a plot from an article about the 30 years of ensemble prediction at ECMWF. You can see also the gradual increase in skill in the ensemble. And it's not only in the medium range, these are both showing medium range weather forecast, what is really the core of our concerns at ECMWF, but it also led to improvements in from days to months ahead. Over the years, the monthly prediction systems have improved. You have here a plot showing for different variables. Blue means better skill for different variables and different weeks between the monthly prediction systems. This is a bit of an old plot, 2018-19 versus 2013 and 14. And similarly, improvement at seasonal scale in terms of ENSO prediction, for example, there is also a gradual increase of the lead time at which an anomaly correlation above 0.9 is reached. So these improvements to the different components, they really brought these revolutions in the different dimensions of NWP, but it's not only in weather forecasts really at different lead times, but the NWP revolution also translates in better reanalysis and monitoring, which are increasingly important. And this is a plot since a while ago, a difference between era 5 and era 6, and which is really nice to show that the improvement in the stratosphere, the smaller difference between observations and the forecast in the stratosphere at the time was attributed to a change in the semi-Lagrangian scheme. So, and this is in particular for the sudden stratospheric warming event. So it's really different components, improving the numerics, improving the physics, improving the data assimilation. They all improve the NWP systems. And it's because the NWP systems are the same systems which are used to do reanalysis, both like era 5, but also the CAMS reanalysis, which are done now by the ECMWF in the Copernicus services. They also benefit from the NWP revolution, and they really lead to very powerful tools for monitoring how our planet is changing. Now, I said earlier that it's hard to disentangle what caused what in the improvement of NWP skill. Our Canadian colleagues attempted such a disentangling because they put maybe less components at one time in their system. So this is an interesting plot from the operational Canadian system. Again, you see the root mean square error in the 500 hectopascal decreasing over time. It means improvement in forecast. And you can see they attributed here the biggest changes were for their system, along with the 4D-VAR and new observations, but really big jumps they had as well when they changed the orographic blocking and boundary layer schemes. So these are physical parameterizations which attempt to represent the effect of unresolved orography features on the large scale circulation. So it's coming a little bit from everywhere, this improvement, but we also know that for different changes to the model led in different improvements. A nice example here from our monthly timescales from our S2 sub-seasonal to seasonal forecasts. It's here when we changed the convection entrainment and shortwave radiation in 2006. This led to an improvement by 6 days in skill for the Madden-Julian oscillation, which is one of the most important modes of variability and which is really important on monthly, but also on seasonal timescales. So we know that that change in convection was the main factor driving this improvement in skill. Similarly, observations obviously play a huge role, and it's hard to disentangle exactly what observation does what, because of course we use lots of observations in the same time. We use hundreds of millions of observations. But what is done generally in the numerical weather prediction system, and this is this exercise to remove some observing systems one by one and see which of them has the biggest effect in isolation on the weather forecast skill. So this is an example from work in the context of the International Year of Polar Prediction, where we removed the Arctic observations and then we looked how much it deteriorated a forecast skill. So what we found at the time is that during summer is the micro observations which play the bigger role, while in winter is the conventional observations. And the red colors here show an increase in the root and the standard deviation, again for geopotential height at 500 hectopascal. At days 3 to 5. So really you can see that removing observations in the Arctic doesn't only affect the Arctic, but it also affects forecast later on in the medium range over Asia, for example, but also over Europe. So it's again a nice illustration of the fact, for example, that what happens in the Arctic doesn't stay in the Arctic, but also that the observations play a crucial role. Another example showing this time the role of data assimilation and 4D-VAR. In the 4D-VAR, one essential component is the linearized version of the physics. which is used in the four-dimensional data assimilation. And this is another of these idealized exercises to see what happened if you would remove that, and you have you don't have a complete linearized physics package, but you have a very simplified one. And again, what you see in terms of key metrics like geopotential height at 500 hectopascal or wind at 200 hectopascal in the tropics, you can see a huge deterioration from day 1 to day 6, basically, of a few percent. So this shows that the way we do data assimilation also matters a lot, obviously, for the initialization of the forecast and for the forecast skill in the medium range. So of course we knew that, but I was trying to find examples where it shows that the different components really play a complementary role in improving forecasts across time ranges. Another component, another thing which contributed to improvements in the forecast skill and also reanalysis is really the coupling of the different Earth system components. So ocean coupling, for example, entered the medium range weather forecast about 2018. And here is just a plot showing the reduction. Blue, it means a reduction in the Rund's-mean square error of wind in the tropics. So coupling with the ocean even in the medium range, it plays a massive role to improve the prediction of winds, for example. But again, components like Arctic sea ice, which also became coupled in the ECMWF system, but also in other systems about end of 2010-ish, like in 18 to 20, also improves both the prediction of the sea ice, but also has an effect in the mid-latitudes. And finally, we know that doing coupled modeling has a big role, obviously, at seasonal and longer timescale. And this is another example of the contribution of improving either the ocean in red or the atmosphere in blue, or the coupled system overall to ENSO prediction between the seasonal system 5 and seasonal system 4 at ECMWF. So a nice example how different pieces of the NWP system contribute really to this gradual improvement in skill. And even if we term it a quiet revolution, I think it's a tremendous advance in forecast skill across time ranges in general in the main NWP systems. And here, obviously, I'm talking about global systems, but the same has happened, obviously, in the regional systems as well, which many of you are using in our member states. Now, the second revolution, the digital revolution, this one is a bit less known maybe, or the term is a bit less known in itself, but what it really is about is really this increase in computing power and going towards pre-exascale, and now with the first exascales computers appearing, for example, the first one in Jupiter, which is here close to us in Bonn, in Jülich, but a one which will be in Paris as well next year, as well, Jules Verne. So as we are going towards higher and higher, bigger and bigger computing facilities, and in Europe now we have the Euro HPC network, which has 3 pre-exascale systems, but also many other very powerful computers. We can enhance the resolution of the system. So as we go from what we are using 10 years ago or so, 20 years ago for weather forecast towards higher and higher resolution at global scale, of course, we can represent better certain elements because we start to partially resolve important phenomena, both for weather and climate timescales. However, of course, this digital revolution as well has you have to make trade-offs, and there is a nice paper of a few years ago as well by Peter Bauer, Peter Dubin, and others at ECMWF and the Swiss colleagues at CSES and ETH, which discusses these trade-offs that if you want to make advances in both science and technology, and the distance here from the center represents the breakthroughs compared to the state of the art, where the potential is coming from, of course, you have to make trade-offs in terms of how much complexity, how much resolution, how many ensemble members on one side, and on the other side, how portable are the codes, what is the system resilience of the supercomputers, and how do we transform our codes fundamentally. And that's why we talk about a revolution, because there has been an ongoing effort in terms of scalability to transform our code so that they can run on these modern architectures, and to do so efficiently, so that we have a good time to energy solution. So of course, what the system design has to take into account all these components. However, on one side, the enhanced computing power, and on the other side, the advances in terms of portability and scalability of the weather and climate codes allow us to start going into the kilometer scale modeling at global scale, which gives not only fascinating illustrations like the ones you can see here, but also gives prospects for significantly improving the realism of these simulations from global to local scale. And this is an example for a project, NextGEMS, in which ECMWF is very strongly involved. This is led by the Max Planck Institute for Meteorology, and the PI being Björn Stevens, and I'm co-leading that together with Björn. And our aim is to build 2 storm and eddy resolving global models, and to use them to look at and explore how the Earth will evolve over the decades ahead. So really do the first multi-decadal simulations at kilometer scales. And by kilometer scales, it's not only in the atmosphere, but really across the components. And what you can see here are some fascinating videos of the wind gusts. You may have seen that if you follow a little bit, in particular the social media. This is becoming the iconic figure done by Nikolai Koldunov at AVI of the wind gusts from 4.5 kilometer simulations with the IFS, coupled with FESOM, the Alfred Wegener Institute ocean model, at as well about 5 kilometers. And the idea is that by coupling the Earth system components at this resolution, you start capturing features that you didn't have before. For example, not only in terms of the wind and the mixed layer in the ocean, but also, for example, in terms of salinity, currents. As you can see here, the difference between FESOM at 5 kilometers and what we use today in operations at ECMWF, which is NEMO with 1/4 degree. But you can also see fascinating features like imprints of the sea ice cracks that you can see here on the 2-meter temperature, on the evaporation. And you can, I mean, we know these things are happening in reality. So it starts to be it's fascinating to start seeing this in the simulations. So NextGEMS is really aiming to build, it's helping to build prototypes from storm and eddy resolving models, from prototypes to take them towards the digital twins we are building in Destination Earth, and I'll end up with that in a few minutes. But first, I wanted to say that the way what we did in NextGEMS, and I think now we are 2.5 years in the project, and we focused on IFS coupled with FESOM and on akin, and we took these models from integrations of a few days, 75 days, and towards the first 30-year runs that were done now at 9 kilometer with IFS and 5 kilometer FESOM and 9 kilometer 10 kilometer akin, but we aim to go even higher as well. And we also had shorter runs, which were of 5 years long, of 5 kilometer simulations with both model. And I really find that fascinating. And there is a whole community now growing around this project. There are other projects as well emerging, like ERI, which are also helping to build this new generation of models. And it's really thanks to all the developments from the quiet revolution and the digital revolution together that we can explore kilometer scale modeling at global scale. And finally, the machine learning revolution, or maybe we should call it a boom, where this plot is very busy, and I don't expect you to read all this paper. There are really references to various papers, but the point is that there is one paper after another showing how artificial intelligence can be used for weather forecast, and focus is now on medium range weather forecast, but there is a growing interest in extended range predictions as well. And it really exploded since end of 2022 when NVIDIA and with their GraphCast model showed the first simulation with their GraphNN model showed that this can be competitive with GFS, but also with the IFS. And the plot is, it's impossible, like Matt Chantry and Peter Dubonnet say it's impossible to keep this figure up, basically, because it just goes at a breathtaking speed. So what are these models showing? Well, they're showing that, for example, GraphCast from Google DeepMind and ForecastNet from NVIDIA are beating conventional weather forecast models in certain deterministic scores, and there are orders of magnitude faster. This is the scorecard, basically, where GraphCast, I think it's compared with the IFS, and actually blue means better. This is in terms of root mean square error, but of course these models are trained to minimize the root mean square error, and they are trained on ERA5. So there is an advantage in showing, they have an advantage in showing the RMS, but still the scorecard looks impressive, and so do the fields themselves. Here is another example from this paper by Kessler et al., where you can see the forecast in ERA5 on which these models are training and the machine learning forecast. And you can see even if there is a smoothing, especially of the fields, especially at the longer lead time, because these models work at a quarter of degree for now, the realism is quite amazing. What's the advantage of using such models, of course, is that the machine learning models are very, you can see here the cost in the unit sense, they cost very little, 0.3 per forecast, compared to 5 billion units to do ERA5 and 180 units to run one of the medium range forecast. So you can see the potential in terms of course, a less computational expense. However, to train the models, of course, you do need supercomputing time, and you in particular need GPUs. So it doesn't come for free. There is a cost for the training, of course. So what can we do with this machine learning revolution, which was started by the big tech? How do we react to that in Europe in particular? So ECMWF, together with our member states, we took action quite rapidly, and this started really in a very close collaboration between us at ECMWF and our member states, really in many weather services, but also academia. And what has happened in the past year, I also find absolutely fascinating, because we saw these papers by the one by NVIDIA and for Christmas. It was released on Christmas Day in 2022. And then basically very rapidly, there was this idea to start a machine learning project, and ECMWF asked, basically, we asked our council last year in June, in June, whether they agreed to start a project of collaborating on machine learning and starting to do this in a more consistent way. That has started thanks to the support of our member states and this collaboration. And what has happened is that, first of all, there were different steps. The first step was to do an evaluation in an operational setting, basically run the existing models, which are open source. So we started running ForecastNet, GraphCast, Pangu weather every day, and we started to display the maps on our website. But we also did basically a review of how good these plots are, and this was a paper which was published last year by many at ECMWF, at looking at their skill score, because in order to improve trust in these models and see actually how good they are, it's important to do a real-time evaluation, like in an operational setup. So run them along our physical models and evaluate them day by day. So that was step number one. Step number two was to build our own version of our integrated forecasting system with AI. We call it AIFS, and this is again in close collaboration with our member states. So this work started in summer 23. and the progress, it went very, very fast. The goal was to build in a few years a probabilistic forecasting system. And by October 23, we already unveiled our very first version of the new AIFS. And now it is, and then we put it on the web along in the open charts alongside the other machine learning models. We also started to compare with the other models, and this plot, it's a little bit small, but I'll have bigger plots on the next slide. And it became rapidly competitive with the other machine learning models out there. And we are gradually working at full speed to improve it. And here you can see a comparison in terms of anomaly correlation at 500 hectopascal with the other models, in particular GraphCast from Google and Pangu, and the physical model. And you can see basically that the new version, the version 2 already, it's a bit better in this respect than the version 1 in cyan, a dark blue versus cyan. But the improvement is even more outstanding in terms of 2-meter temperature. This is against observations. And you can see here the improvement we had between our very first version and the new version, which in terms of 2-meter temperature RMS across North Hemisphere, it's better than the physical model. Moreover, we also added precipitation, which the other models didn't have yet, but I think Google may have it, DeepMind may have it now. And there again, it's also remarkable to see that the SIP score is better from the AIFS. The third step, which is also important, is that you can all explore the AIFS data yourself, because these models are very exciting, but we also have to basically examine them. So we have made the AIFS charts and data open on our website, and you can look afterwards at the slides for details of how can you access it. And it would be great to have the feedback on how the AIFS is performing. And finally, the real goal is to do ensembles, and we started there as well. And there again, these are very early results where we also apply uncertainty in the AIFS, and it's not as good as the real ensemble. Here you see a classical spread skill relationship in black for the physical model ensemble, our operational ensemble, and in orange for the AIFS. And you can see that the skill is not matching the spread. There is a gap between the two in the AIFS, but I think we are definitely on the right track. So I talked about the quiet revolution, the digital revolution, and the machine learning revolution, very accelerated revolution. Where are we next? How can we synergize these three revolutions to go towards better predictions and system predictions, which is our aim, which is what all of us are interested in. And I'll give an example from Destination S, which is looking at synergizing these three revolutions and to build digital twins of the Earth to complement really the existing capabilities we have in the national Met services, at ECMWF, but also in the Copernicus services. So why I'm saying that Destination S is synergizing these three revolutions is because it's really building on these capabilities we have jointly developed in Europe, and it's really taking advantage of the power of the Euro HPC computers, which are among the biggest in the world. It's using Lumi in Finland, which is number 5 in the top 500, Leonardo, which is number 6 in top 500 in Italy, and Mare Nostrum 5, which is upcoming, which is number 8 in top 500, but also Meluxina in Luxembourg. And what Destination S, what it's trying to do, it's an initiative of the European Commission over a period of several years. We just had the first phase, and now it will end in June. It started in December 21, so we are 2 years within this initiative. It's implemented by us at ECMWF in collaboration with many of you. We collaborate with over 70 institutions across Europe, and together with our partners at ESA and EUMETSAT. And it's looking at really establishing bespoke cutting-edge simulation capabilities using these facilities of the EuroHPC, and at providing information at scales where the impacts of extreme events and climate change are felt. But it's also fostering an innovative and thriving AI-enabled digital ecosystem, which aims at exploiting this data for creating new tools to complement the tools we already have to support decision-making in order to better respond and adapt to the challenges posed by extreme events and climate change. So this is my attempt to summarize the current systems and where Destination Earth is going and what are the steps forward. So we've made, as I said, great advances in terms of Earth system models and observations, and in modeling the impact sector and in working with users. However, the resolutions are still limited, as we know. The global ECMWF forecasts are today at 9 kilometers. The regional simulation, the regional forecasts are at a couple of 1 or 2 kilometers. Of course, there are still small-scale processes which are not represented. This is even more true for the climate, where the climate models of today, the global models, are at resolutions of 100 kilometers, or at best in the high-res MIP context at about 25 to 50 kilometers. There are limited ways to change the experimental design or output, and there are limited versatility to access and interact with the data. And there are, of course, predefined configurations and simulation times. In particular, for climate, in the CMIP scenario, we run the climate models every 7 years or so. Now, what Destination Earth is aiming to do is to bring these different elements a bit further, exploiting the revolutions we have in the richness of the observations and NWP systems which we have now. And what it's trying to do is to go towards more interactivity for the user, and for that, it's working in co-design. We are trying to work with co-design with users from the start through a co-design approach for selected use cases. It's exploiting the EuroHPC power to go towards higher resolution in order to provide higher quality global information with local granularity. But it's also trying to bring the impact sector models and impact sector models within the same workflow, and to really provide information both continuously, but also more flexibly and on-demand production, and to stream data towards observations, towards applications as we go. So the different roles of the different institutions in this is that ECMWF is building 2 digital twins, the first 2 high-priority digital twins, and a software infrastructure, which we term as the digital twin engine, which aims to really bring together these different the digital twins and allow users to interact with their data. EUMETSAT is putting in place the data lake, which gathers the digital twin data and many other data sources. And ESA is building the core platform, which will allow users to access the digital twin data and these different data sources and use it to complement their current decision-making capabilities. And the system will open to users from summer this year, when we are entering the second phase of Destination Earth. Now, just very quickly, the first 2 digital twins that we are building at ECMWF in collaboration with our partners throughout Europe are focusing on climate change adaptation, and the idea is to provide support for policymakers for adaptation on multi-decadal timescales. It's implemented by CSC in Finland, together with many partners across Europe, in particular climate modeling centers like BSC, the Alfred Wegener Institute, and the Max Planck Institute in Hamburg. And the second twin is the weather-induced extremes digital twin, which has 2 components: a global component done at ECMWF with the integrated forecasting system, and a regional component allowing to zoom over Europe on demand, in which many med services are involved and which is led by Meteo France. And this is focusing on timescale of a few days ahead. So just a few words to say that what we are doing at the moment in the climate DT is really running the first end-to-end climate DT workflow on Lumi in Finland, including selected applications with our two models, IFS NEMO and ICON, and IFS FESOM will follow at 5 kilometer resolution, both in the atmosphere and in the ocean, which I think it's absolutely fascinating. You see here a nice video again showing the resolution of today, 100 kilometers versus 5 kilometers. So this digital twin will provide information globally at these scales, and it's using the models developed in the project that I talked earlier, NextGEMS, which underpin the climate digital twin. And the idea is to really stream information, not only produce weather, like the Earth system information, but also produce tailored information for applications. And this is a nice example where it's producing weekly PDFs of wind speed, which can be translated in capacity factor for wind turbines, really in every point of the globe at this 5 kilometer resolution, which can be very useful for optimizing wind farms, for example, portfolios, for example. And finally, the weather-induced extreme DT, it's really this magnifying glass on extreme events to really complement our current capability. At the moment, we are running IFS globally at 4.5 kilometers on Lumi, and our partners from Meteo France and many weather services and academia involved are building this zoom over Europe with a translatable domain which can be moved as a storm evolves, for example, or when a pollution event happens, for example, zooming over a region. And this is really nicely complementing the capabilities we have today, and it will be at resolutions between 500 and 700 meters. And I'll skip this pretty animation because I realized I was already longer than I promised Ernesto and colleagues to be. But just to say that it's important not only to do these high resolution simulations and bring the impact sector information in the same workflow, but it's really important to do this with a modular and performance software environment structure. And that's what we do at ECMWF, again, together with many of you, and we term the digital twin engine, which is really a software environment which allows to run both the weather and the climate DT, of course, tailored to each specificity of each of them, but allows really to ensure that these complex simulations are run efficiently on EuroHPC and that we can really power the digital twins, but also manage and interact with their data. And of course, the machine learning is playing an increasingly important role, and it's also important to have the pipelines to be able to train, for example, the machine learning models from the digital twin data, and this is something we are going to focus on, complementing what we do together already within Destination Earth. So finally, I arrived to my conclusions. What have we learned and what's next? I think I would say that we learned that is through the quiet revolution, the steady investment and leadership in Europe in Earth system modeling and Earth system observations has made a difference. We have learned from the digital revolution that conventional models need to be future-proofed via new software and hardware standards to be able to run them, in particular on the mixed architectures. The large-scale efforts to make kilometer-scale models today, this make this possible, and in particular in these large collaborative frameworks like NextGEMS and Destination Earth, where Europe really has an edge in this tradition of collaboration we have in Europe in order to make things advance. And I really think this will make a difference. The machine learning revolution, it's breathtaking. A PhD student today can write a machine learning tool that can beat in certain metrics the best weather prediction models in the world based on hundreds of years of personal developments. And it's important that we look at the data is open so that we examine these models, and it will make it easy to use to make progress and to analyze what are their pros and cons, and how do we make best of the physical models and machine learning models. From our point of view at ECMWF, it's clear that we have to find ways of combining these two types of powerful tools to continue to deliver the best possible weather and climate predictions. So what is next? I think the key will be how we combine these different elements, because the models will be better, the weather and climate predictions will get closer. This is what you also see in DestinE, where we use the same software tools, but also the same models and the same resolutions for weather and climate. I find this utterly fascinating, because we can learn things and we can develop models faster if we look at errors in both at both timescales. The tools will become easier to use. The data and tools are looking into how to make easy use of this amazing amounts of data. DestinE will produce 1 peta per day. If you think about it, it's really another level compared to what we were used a few decades ago. And the HPC and data will be federated, and it is federated in a way. That's what EuroHPC is doing, and that's why also DestinE, it's a blueprint of how do we do run weather and climate in a distributed computing environment. But all this needs the people and needs collaboration. And I think, again, I want to repeat that that's where I think Europe really has an edge, and programs such as DestinE, which bring hundreds of, more than 100 institutions in 2 years, together with the 3 international institutions, ESA, ECMWF, and EUMETSAT together. I think it's really bringing, it's a new way of bringing the European meteorological infrastructure to together so that we can advance faster. And with that, I will thank you. I apologize, I was a bit too long, and I would particularly like to thank Peter Dubin and Matt Chantry, who provided most of the material you saw in my talk. Thank you.
Thank you, Irina, for this fascinating travel describing the past evolution and revolutions of NWP and the perspective for the future. And now we'll move very quickly to the questions. Vesna, could you please tell us the first question?
There are no questions at the moment yet.
At the moment. So I will ask myself a first question. We know that the current observation capabilities are inadequate for the new generation of high resolution models. So new sources of data are needed, including not only new instruments and new observing platforms, but also extraction of meteorological information from data obtained for non-meteorological purposes. Could you comment, Irina, on that question related with new observations?
Sure, I think observations, as I said, are playing a key role, and it's important. Also, new observations like from citizen data or from crowdsourced information, but also higher resolution observations are important as we go at these scales. But I think it's also very important to make better use of existing observations. This is also what we looked about, in particular in DestinE a little bit as well. We started, but more general at ECMWF is, for example, how you've seen the satellite observations, how you go, and that going to less thinning as you increase the resolution in the data assimilation, for example. And there is a lot of winning, there is a lot to win from there as well. So we definitely need to make better use of existing observations and complement that with new observations where they are needed.
Thank you. Vesna?
Stencil Chachkovsky, if I pronounce it right, ask, can you say a few words about ERA 6 that is meant to come out during the year?
I'm afraid afraid I can't give particular details on ERA 6 because it will come out next year, as far as I know. We are working on the configuration. I mean, the only thing I can say is that we are working now on a cycle which is finalized, which is 49R2, which will be used for ERA 6, but it will go towards higher resolution. The resolution, I don't think it was completely finalized yet, but it is looking in the range of, I think, something like 14 to 18 kilometers, something like this. But it may, as again, the resolution was not fixed yet. And the idea is to also use coupled modeling and in the data assimilation, but the configuration is finalized. So I think that's all I can say at the moment. But it will use the latest cycle, and even the cycle which is ahead of the current operational cycle now. So we are still building the cycle for ERA 6.
Thank you. Reza Kandan asked, is it supposed to use cloud infrastructure like Amazon Web Services, Microsoft Azure, or Google GCP in destination Earth, since they have wonderful tools for machine learning?
No, so it's not going to use these commercial cloud providers. ESA are developing a cloud platform, but which is called the Destination Earth core platform, and this is going to provide as well capabilities for machine learning, together as well with the data lakes that EUMETSAT is putting in place, which also will have some capabilities for training machine learning models. But the interface, basically, the digital twins are running on the EuroHPC, and then there is a infrastructure layer which is built in Destination Earth with data bridges co-located with the EuroHPC site, where the data from the digital twins and other sources of data will be synced in, federated with, and then there will be this core platform, which will also be a cloud platform, but a separate one, not Google or Amazon.
Thank you. Christina Primo asked, how do you currently create the AIFC ensembles in your experiments? For example, in the plot where spread skills was compared.
I am afraid I can't answer that question. There was more to say because I don't know the details, and you would have to ask Matt Chantry and colleagues who are leading this development. But what I understood so far is that they are perturbing not only the initial condition, what they were doing at the beginning, but they are also they have a trained model uncertainty. But I can't tell you more at the moment. I'm sorry.
Then Svante Bodin said, I am very much impressed by the progress in European cooperation. But what is happening in the US on similar themes?
Things are happening in the US in the sense there are several groups around the world which are looking at doing in particular kilometer scale modeling. Of course, in the US, but also in other countries. You know, of course, but it's less organized. That's why I was insisting on this cooperation in Europe, which is really important. You know, different centers in the US are building their own models, and they work less towards common models and common tools. And I think that's where Europe is really playing a key role with the European funding, which is complemented what all of us do already. And for example, through Horizon programs, through Destination Earth, through Copernicus, which are fostering this European collaboration on top of the collaboration where obviously all of us collaborate in the frame of the European meteorological infrastructure.
Okay, and then one more. Beatriz Gutierrez, you said PhD students will be able to build their own models. So how are you going to support this future research? Will it be possible to use your cloud supercomputers to make trials? Will you open workshops about coding to understand better how to build digital twins in higher resolution scales and not globally?
It's a good question. Training, it's a complex question. I think what I can say is training, it's an important element. It's important to train a new generation of early career scientists, in particular with respect to the AI. ECMWF has done a MOOC last year. I don't know if you know, a massive open course, and we'll do another one in the framework of DestinE on AI. This is really enabling to share the knowledge. There are different workshops. There are different events about machine learning in particular. I think your question was in particular about that. There are, of course, what's important as well, that the models are open source so that people can, and that we share the tools and the knowledge. And ECMWF has a Git AI hub. You can have a look there. Maybe I can post the link somewhere afterwards. Have a bit of a look there, and we are trying to exactly to go in that direction. We can always do more, of course, but I think it's important that all of us we develop similar tools, and we develop the tools in collaboration so that you don't develop duplicate work. Whether it's possible to make trials, I mean, that's the idea of the core platform of ESA, is that people can go on the core platform and do different things there, but I can't give more details at the moment on that. But ESA will make announcements fairly soon about what will be possible in destinations to do on that platform. But there is also the European Weather Cloud as well, where many of the member states have access, and that's also good to experiment with these different things. And about it, just a word about the digital twins at high resolution scales, not only globally. There are different categories of digital twins. The ones we do in Destination Earth are the Earth System digital twins, which are the two global ones, the weather and climate global. But then there is also this zoom, which goes across meteorology, but also impact sector elements, done over Europe at regional scale by our partners from Meteo France and from many services. They are not only global. Then, of course, there are different, more smaller digital twins, which could couple with the big twins in this ecosystem, using the input data and creating digital twins at local scale. And that can be those I would call application twins. And that in Destination Earth maybe can also happen on the platform.
Okay, thank you. I think this is the last question, Vesna, isn't it?
Yes.
Yeah.
Yes. You're
Okay.
right.
Let me finally thank Irina for her for this motivating talk, and it was really very, very interesting, and everyone for attending and for participating in this event. And let me also repeat again my invitation to submit ideas for further topics or speakers. You can send them to the EMS Secretariat or any other via. And thanks for participating, and that's all from my side. Thank you.
Thank you very much for listening. Thank you very much for listening and for the invitation.
Thank you.